And we are live.
Hey everyone, welcome to another live science stream. We're continuing with our fellow research roundtables. So this is a way for us to convene and discuss research that we've been doing over the past week, though with the caveat that we usually restrict ourselves to developments that are kind of computational in nature. So sometimes we'll spend a week doing say, a theoretical review or trying to understand some concept, and then we probably won't have like theoretical lectures that are like long-winded during these discussions, but we certainly will have discussions of key results or new concrete things that were done. So I think when I was just getting on the Zoom, I saw Carlos and Nick doing some quick piece of surgery on some piece of code. So I gather that they have something to show. Um, I know that Wukash and I have been in the trenches, um, finalizing our understanding of how these L groups function and doing a little bit of review of Lie theory. So probably like by next week or the week after, that will translate into some real visualizations and computational examples. But we're not quite there yet. Richard, do you have other things that you want to show during this roundtable too?
Yeah, we have one tomorrow also, right?
Tomorrow's
We have a
community forum.
community we
Oh,
have a
community. Oh, it's
community
a
forum
community forum.
tomorrow.
Yeah. So I have a few things. My section will be fairly brief. I have a couple of papers that I've found that are quite interesting and some computations from the last week. So yeah, but mine shouldn't take more than 10 minutes or something.
Yeah, so I think we can probably fill the hour or so.
For sure.
So without any further delay, uh, Nick, Carlos, shall we begin?
Yeah, we can start. So it's mostly my presentation. I was just asking a quick question to Nick. He has done the good work beforehand, and it was basically ready
That's
for me
why
to use.
that's why I refer to both of you guys because I know it's a kind of a joint
Yeah,
effort, even if Carlos is presenting.
yeah.
Yeah.
But I just wanted to say that maybe Nick has something that he wants to share or
Hmm.
some other. I don't know if you've got
Well,
something else.
I'm not sure. I'm on some exciting functions. I know that Einstein summation that we
Yeah, actually, you might actually
can't
maybe okay.
probably.
Let me present and then you can maybe follow up with that because that's a good segue in the end.
Yeah, okay.
Okay. So let me share the screen on my tablet. I'll show. So I'll give a quick theoretical or perhaps more conceptual summary of what we have done. Okay. So there is this long time ago. I mentioned this duality between rewriting and algebra that we wanted to use quite explicitly in a long
Hmm.
time, meaning in the time scale of our work, which is like 3 or 4
Yeah.
weeks. um,
Oh,
so, yeah, I mentioned this duality between algebra and rewriting, and that we wanted to exploit in our research, and basically today we have the basic functionality to be able to implement this and to be able to computationally operate with this kind of concept. So let me remind our viewers and ourselves what this is. So the situation is as follows. So we begin with let's do a graph, and I'll show you the functionality because I've tested it for graphs because it's the most visually clear for now. So if we begin with a graph, something might look like this. We'll see directed examples because that's how we've built the function so far. But so if we have something that looks like a graph, and we're thinking of rewriting. We think of two possible paths. So on the one hand, we can think of the dual, the algebraic duals in some sense, which you go and you have your adjacency matrix. So I don't know. And you have your ones and zeros. So whatever, some ones, some zeros, whatever they are, right? And we basically have this equivalence between the two. These are two equivalent ways to present the graph. So if I call this G, for example, and I call this A, there is a very obvious operation that we can do with A, which is to square it, right?
Mm-hmm.
So just take matrices, they have a natural algebraic structure, and we use that algebraic structure, and we could do things like on the same set of vertices, two graphs, A and B, and we could do A times B, and it could be a bit more sophisticated. For now, let's just think of a single graph and just take a square. So you square A, you get A squared, which again is it's a matrix of the same kind. So it's 1, 2, 3, 4, 1, 2, 3, 4, whatever, and it has ones and zeros somewhere else, whatever. So we have the same kind of object. So of course we can come back and draw. So this is going to be a graph on the same set of vertices, because it's a square matrix of the same dimensions. And we discussed before, and the viewers probably remember, that we have a way to interpret this operation, the precise way in which we're going to write the edges of our graph after taking the square is precisely related to something like a motif rewriting on our graph, right? So let me just draw the edges that will come. So maybe if I use a different color, it will be clearer. Actually, let me just use white here. So this one will be this one, and it will be, let me make them directed because it's going to be simpler than actually the example that I'm going to show. So it will be this one, and this one, right? So some of them, right? It's another graph. It looks similar. It looks the same kind of object. So this operation is all fine and good. This is very common in graph theory and network theory. This is the usual, the entire spectral theory is based around this sort of algebraic operation where you're doing this algebraic construction. Now the observation that we had a few weeks ago, and that I've been trying to implement, I've been trying to promote as our tool, and it connects with the philosophy, the more sort of Wolfram sphere philosophy of rewriting, is that in order to close this commutative diagram, so we have an arrow that takes us from this graph to, so let's call this G prime, that takes us from G to G prime in this diagram. The operation that we have to do has to do with rewriting, right? And essentially the way it works, as we've discussed a few times already, is, I'll draw it in yellow as kind of the pattern that happens, is if you match this pattern, where you find three vertices that appear exactly in this configuration, then you should rewrite, maybe with directions, because that's what we're doing. Then you should rewrite the same vertices, but write that one down. And the connective tissue of these two equivalences, and by the way, so what's happening, just to explain the arrow, what's happening in this arrow is that we are taking the initial hypergraph, we are applying the rule in all the positions that applies, right?
Mm-hmm.
And we are just rewriting on those positions, right? So we just applied everywhere and only once. So it's always position, application, position, application, position, application. We never, so this is what I call a one pass rewriting, right? So you do one pass, and you don't do consecutive rewriting. It's only the sort of the first shell of the causal graph of rewrites that would be generated, right? So that one pass is this G prime. So this G prime equals the sort of quote unquote one pass function of G. And the one pass, of course, depends on the rule. So there's some rule here, R, and R is given by this. right? Okay, so on the other side here, we all know that what's happening in this algebraic operation. I didn't write it, but might be useful. So that you do P over G of AIP times APJ, right? So this is an indexed object IJ, and that's the square. So the entire this duality. I mean, I wanted to have this diagram sort of shown this way because I've said this before, but just as a reminder, this is the duality that I'm trying to propose, right? So there is rewrite. There is this idea of doing a one pass, and that corresponds exactly to taking the square of your graph. And the reason why I want to flesh this out in this way is that normally you see the rule on one side, and you take a very computational or very sort of automaton kind of mentality, and you say, all right, where can I apply it? It changes things, so you have a multi-way graph, sort of a rewrite system kind of philosophy. Or you take the algebraic perspective in which you have objects that operate, and you have some associative property you can exploit, and blah blah blah. So this is trying to kind of marry these two approaches, and by that we accomplish this construction of the one pass construction, which effectively takes a graph, provided a rule, takes a graph and just outputs a new graph, right? So this is very obviously very well known, nothing new, everything is classic for graphs, but our goal is to do this for hypergraphs and be able to use non-standard patterns and to try to match motifs that are much more general than this. And so, by the way, to just completely close the loop in what I'm trying to say, all this stuff eventually leads to some spectral theory. In this case, is the standard spectral theory, because we have one operation, one algebraic operation, and we have matrices. We know how to deal with these objects. Now, the idea is if you take a different motif, you would lead into another spectral theory. So the standard spectral theory can be associated with this particular rule. So in some sense, this is R spectral theory, where R means that particular rule of the V motif mapped into this particular way, right? So what we have been doing is in building our functions, our hypergraph functions, we've tried to get enough functionality so that we can finally do these things computationally, and that's the thing that I want to show. So I'm gonna try and loop back to my desktop.
Well, you really have a talent for creating suspense.
I mean, it's nothing super fancy. It's just that we can do that stuff now.
That only adds to the suspense. The modesty adds to the suspense. It's just a little functionality. No big deal.
Okay, hypergraph rewriting. So, I mean, most of this is just cosmetic. So I'm going to show. I mean, we can play around, and maybe we can do another example if we feel curious. Wait. I have to run this again. So, yeah, let me just. Anyway, so.
Can anyone see? Is anyone having trouble seeing the?
Yeah. This is not the point. I just want to draw this here. I'll have proper.
I just wish I could see it.
High contrast thing in a second.
Or you can do the default color white.
Yeah, I know. But this is all the stuff that we just fixed. So let me get rid of all this stuff here. Okay, so this is the functionality implementation that we have now for rewrite rules. This is some test graph, so we can. I mean, I have conveniently our hypergraph draw function here in this beautiful editor, and we can basically. What I do is I create the hypergraph here. I copy clicking here, and I'll just paste it on the right positions. It's very convenient, and I was really eager to be able to communicate. This is already working. I can no longer have to type in edges. I can just like literally draw them. This is already quite nice. I'm quite excited about that. But here's the first use I've made of the function that Nick has been working on, the hypergraph rule function. And as you can see, this is basically what I was trying to draw in the blackboard, right? So I have some initial state test graph, but then what we have is an input, an output, and then the rule is implemented as, we call it test rule, and now we can apply that as to a hypergraph as a function in Wolfram language. And so, let's try that. Let's try to do exactly what we looked at. So, this function, one pass rewriting, that's what I explained. So it applies the rewrite rule, so a given rule to a given hypergraph. It's very straightforward, and it just does this one pass rewriting. So it applies to in all hits for the pattern matching where the rule applies, and it just rewrites according to that, and basically gathers the output edges, and it presents the hypergraph that results from a single rule application on each hit position, on each pattern matched position, right? So as we should expect, if we have this pattern, right, the 1, 2, 3 path, if we rewrite with this, which basically is the path composition, we should get an arrow from 1, 3 and an arrow from 2, 4, and that's exactly what we'll get, right? So this is the output hypergraph. Now, that's one half of the square in the duality that I was presenting. That's the rewrite square. Now the algebraic square is we need to take the adjacency matrix of our hypergraph. So so we have hyper matrix as a function. So I could do this on test graph. And it outputs an object that, I think there's just a picture, isn't it, Nick? There's sort of kind of showing the nature of the thing.
That's a picture.
Yeah.
But if you do the traditional form, it kind of shows.
Yeah.
Not not the input form. Instead of I, press T.
T?
T, yeah, for traditional.
Oops. Okay, there we go. So that's exactly what we should expect, right? We have 1, 2, 3, 4. That's the edges that should be highlighted, right? It's showing the single matrix that is in the graph. For this particular application, I used Tensor, and this is where I think Nick can present the stuff that he's been doing, because the whole point is to implement arbitrary operations. So basically, the slogan here is, this one is redundant, is to, I have to run this again. No. Oh, because I have to copy this. Sorry, apologies. I have to copy this. Hypergraph, yes, should be. Yeah. So what this is doing is it's taking the adjacency hypermatrix of our graph, which in this case of a graph just looks like that, and then it's taking the square, so B is just the square. We're just using the basic matrix algebra of Wolfram language, and now we are using this function hypermatrix graph, which gives you a hypergraph object from a hypermatrix object, basically. So as far as I understand, Nick, the hypermatrix object is basically a list of tensors, right?
Yeah, that can be.
Yeah. So this list here, list of a single tensor, I just did here for the purpose of demonstration that we're going to do with a single graph. But it outputs the hypergraph, and here I just had this hyper cool matrix graph to be able to have the correct coordinates and to display it nicely. But the whole point is that this is the same as this, so the commutative square is complete, and so we finally have the rewriting algebra duality implemented functionally, and so we are computationally ready to study this complete arbitrary motif rewriting and to start exploring in that direction. So the one thing that we need to do, and I think Nick has something to say about it, is it will be ideal, also as a desideratum for further development, it would be ideal to have, because this kind of shows that it really doesn't matter whether you think of taking algebraic multiplication or doing these one-pass rewritings, right? These are kind of one and the same constructions, right? So it would be very nice to be able, in the same way that you have this editor, you can just actually edit your algebraic operation. Because for now we will have to, here I just wrote a.a because just happened to be matrix multiplication, like ordinary matrix multiplication. But for something like the fish rewriting or the three triangles rewriting, like the cone rewriting and things like that, you're gonna have to use some kind of tensor contractions and some more complicated tensor algebra formula, right? So one of the direct outputs of this is that we will be able to encapsulate entire tensor algebras in a single motif, which is what you rewrite in your rule, right? So that's something quite powerful, and so, but this required that the Einstein summation function that we're going to use to actually implement the tensors sum over more than two indices at the same time, and I think Nick can show something along those lines.
Okay, good setup. Well, by the way, though, before we continue, Richard had a comment. Richard, you're live on the call. You can just say something.
I thought it's better to wait until a sort of stopping point.
Yeah. Okay, go ahead.
So I made a kind of analogy to how people can sort of implement cellular automata with convolutions and rectifier functions. You can end up doing the kind of pattern matching and rewriting, with those operations rather than the traditional way, which is just matching based on the Boolean value of a group of cells. And so my understanding is we're sort of doing something quite similar. We're using sort of we're applying functions to these adjacency structures in order to implement the rewriting, the rule matching and rewriting in one go, right? Please correct me if I'm wrong, because the rest of what I'm about to ask is sort of based on that assumption.
Okay, wait. So say it again. So you say that we are trying to.
So in this example, we've got this. You've made the observation that squaring A was equivalent to the rewrite.
Yeah.
Is that right? So.
Yeah. That's right.
And in the general case, what do you expect? So for any kind of arbitrary rule, what will the sort of algebraic operations look like for sort of arbitrary rules?
Yeah, arbitrary. So that's a very natural question. So kind of part of the point that I'm trying to make is that arbitrary operations are extremely special because
perhaps they could be composed from sort of simpler algebraic operations and achieve the same thing. But the one problem I have with it is also that some rules sort of introduce new vertices. So I can't quite see how that fits in. So it's probably trivial.
No. So this is, it's not trivial at all. This is what you're pointing at is precisely why I want to take more the rewrite perspective than the algebraic perspective, because I've approached this as an algebraist for all the time that I've thought about higher order algebra, and my path was coming from pure algebra into hypergraph, eventually into rewrite theory of hypergraphs, precisely because you realize that these algebraic operations are very special situations where you can do these one-pass rewrites. It happens that what you end up with is of the same order as your initial data, and they happen to live on the same set of vertices. The fact that you have more or less vertices is not so relevant as long as you don't have new ones. That's not so relevant. But yes, so these are extremely special situations. So what you have is, when I said duality, of course, there's some degree of sort of quotienting going on. So it's a duality between the algebraic structures that you can make on the matrix side, and some very special class of rewriting constructions.
Gotcha.
Right.
Because in some cases you also have like the permutation of the the entries in this tensor will affect things, and as I say, this example of you take cellular automata, the initial things with like, oh, what happens if we train some neural net? It is interesting that just convolutions, which are essentially little pattern matchers, could actually sort of function as a kind of rule matcher. But how to extend that to the graph and hypergraph case, I'm not sure, because you don't have this locality property, which you do in the sort of cellular case. Instead we can permute the entries as we like. And this is why previously I had mentioned this fractional isomorphism thing, which is a kind of relaxation of standard isomorphism, where you take sort of random matrices of your original matrix, and it's sort of closely related. But anyway, I think that's all I wanted to.
So does that answer the question? Because I think there was a question at some point, and I.
Yeah, no, it does. I see. Yeah, exactly what you're stating, which is some rules have exact analogs in the algebraic implementation.
Yeah, the whole point is, remember, we're trying to go after some kind of spectral theory generalization, and the entire point is to see that spectral theory is formulated algebraically. That's where it comes from, right? I mean, it's a eminently algebraic theory, and I mean, it's based on equations that depend on the algebraic operations that you perform. So the whole point is illustrating that you have the entire algebra story in the rewrite side, but you have more in the rewrite side. So in a way, it's kind of my justification for saying all we need is a very robust theory of hypergraph rewriting, and quite sophisticated with labelings and things like that. So for example, something that I've mentioned in the past, that labelings are important. If you want to do something like actual algebra and have something like a times b, because I mean we just did a squared, right? But if you want a times b, what you need is some kind of edge labeling, so that you have edges that are labeled over some color or something like that, other edges that are labeled over some other color, and your actual rewrite rule says that this edge must be from A and this edge must be from B, right? You need, the order of the pattern matching also takes into account this sort of color or, labeling.
Yep.
And that's where you can faithfully encode algebra in this general rewrite theory. And of course, the goal is eventually these hypergraphs are going to be diagrams for general formal systems. And the idea is that those rewrite rules are going to implement some sort of algebraic behavior. At this point, we're just saying the natural algebra that was attributed to graphs historically, I guess, turns out to be quite natural if you find the right constructions on the rewrite side. The right construction here is this one pass idea. I mean, nobody's telling you to do this one pass. I mean, some people might be confused to think that the information is in the rule, in the rewrite rule, or is in the fact that you are taking square or something like that. The information really is in the fact that you're doing this one pass, where you look at your initial state, you apply the rule in all the possible positions, and you only look at the outcome of those the aggregate of those independent applications, right? But you never update your state and apply the rule again, which is kind of more the rewriting theory mentality, right? So you do this one pass construction is just something you can do. There's nothing, nothing stopping you from doing that construction.
It's more global, Yeah.
I see. And doing that is the dual to algebra. That's the point here, right? It's doing that kind of on the eyes of rewrite theorists is like, that's kind of a bit unnatural, because the whole point is that you can rewrite and things can change locally without changing locally, blah, 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 all that stuff. That's great. But to recover algebra, we need to do that, right? So that's the duality. Duality is between this one pass kind of single application of the rewrite rule with taking something like a square or doing a binary operation in this particular case, right? And there's the whole thing is that there's an interesting interplay between the arity of the operation, for example, and the topology and the cardinality of your rule, right? The cardinality of the hypergraphs involved in your rule and things like that. So the algebra side talks about arity and bracketing and trees of expressions and so on. And the rewrite side talks about different things. But these all are all translatable, and that's kind of the program here. We're trying to develop that correspondence and to exploit it, so that when you can formulate a spectral question on the algebra side, you can go to the rewrite side and just answer it in more computationally straightforward ways, right?
Nice. Thanks.
Yeah. Any more comments, questions on this? Otherwise, we can see what Nick has to offer.
Do you expect like exponential to be some simple rules?
Yeah, I mean, that's a good question. I mean, obviously, you will apply these things iteratively to get powers. So, in my mind, this construction is like almost indistinguishable from any kind of construction that, given a graph, gives you another graph.
Mm.
So you can just iterate it, and it can evolve in complicated ways. I guess, let me put it this way. Yeah, there is this very simplistic view that we've always mentioned, where you can take the entire graph, the entire initial state, and you can take the subgraph, the subhypergraph of the union of all the locations where the rule applies, right? And you define a rule that is literally take all that and rewrite it to the output of your rule, right? So in that way, you can actually reduce this one pass rewriting operation to a single rewrite. So you become, it's a very stupid thing to do, because that's going to be, that's going to create a different hypergraph, and nothing is going to match in general. So it's very non-parsimonious, but you can technically think of it in that way. So you're never really leaving the rewrite space, right? You're never leaving the rewrite formalism, but yeah. So effectively, it's just a function that takes an input, gives you an output. There's nothing too mysterious there.
Yeah, and how do you handle not Boolean matrices?
I mean, that's just there's no real dependence on the fact that these are Boolean, because you use the rewriting is, if you have something, what is a non-Boolean matrix on the graph side? You have to answer that question first, right? So you have
like do you have a model as a rewriting system for general matrices?
So
or an idea?
So, well, yes, there are different fields and different algebraic values have different representations, right? So if you have this is just Boolean. If you go integer, then you go from graphs to multigraphs. If you go to naturals, you go from graphs to multigraphs. If you go to integers, you go from graphs to signed multigraphs, right? Mm-hmm. And so on, right? Like you can develop very natural.
So you basically have weights on your edges, right?
If you want to, that's one way to see it.
But will it be one simple rule if you want to implement this way, like the real matrix multiplication?
But the real matrix multiplication is the same as any other matrix multiplication.
Yeah, but will it translate to a simpler rule if you now have all these weights on your edges? Wouldn't it be some very complicated rule depending on weights and stuff? Because it may be it.
Matrix multiplication really is just that rule. Because if you have of course, the way that your weights are going to combine will need to be specified somehow. The rewriting will have to rewrite the information carried by the edges, which kind of takes away a little bit from the beauty of doing just rewriting. But in some technical sense, these things are more like deep observations than results in some sense, right? These are just saying rewriting on the one hand or taking algebraic operations on the other are essentially the same thing, and it's just a matter of which framework is more convenient to think about certain problems than making any bold statements about something quite deep. It's more about it will be very efficient.
I'm just worried that the rewrite rules may become very complicated if you have like complicated ring that you build your matrix over.
Sure. I mean, if your goal is to have matrices over like infinite fields and things like that, I have no idea how that's going to translate into the rewrite rule on the other side. But the point is that's not what this is for. In some sense, right? Like the whole point of this is not to take your favorite matrix ring and then give it a rewriting theory expression. The point of this is that you have direct ways to translate algebraic information like spectra into rewriting information, right? And for that you can make analogs and you can try and generalize, but the point is for this to be everything should be discrete, everything should be finite. I mean because this entire thing is intended for diagrammatic calculi, right? So it's not, I mean, you really want to stay away from infinitary stuff, because that's kind of the whole point of diagrammatic calculi, that is going to encode infinitary mathematics. It's not going to be the infinitary mathematics, it's going to be the symbols that explain infinitary mathematics, or any kind of mathematics, of course, but in particular infinitary mathematics, right? So it's kind of, we're designing the language here. It's kind of mathematical language design, right? It's more than mathematics itself, right? That's why we are kind of staying away from the full generality of, okay, I can have any ring of matrices, let's find its rewrite tool, right? We're trying to be much more constrained and focused than that. But it's a valid question. I mean, it's a mathematically valid question, of course.
Yeah, like I love the idea. I love the idea.
Sure.
It's rewriting, but
And it's
I would like to really see like real matrix multiplication implemented in this way, and if the rules become more complicated, or you just.
I mean, I can tell you exactly what the rule is. I mean, the rule is you have your weights are real numbers instead of one, and so when you rewrite, you need to specify, the given the pattern matching becomes any variable. You have this shape that I have on the screen, right? And you have any variable weight on the first edge x and any variable weight on the second edge y, right? And basically you're doing the rewrite by writing. So, well, if it's matrix multiplication, then you're going to be doing something other than just one pass rewriting, because you actually want to add. So you want to do additive one pass rewriting or something like that, right? Where you do the one pass rewriting where the weight of the new edge depends on the weights of the two former edges by multiplication, x times y, right? And then you end up with a multigraph, and multigraphs and additive graphs are the same thing, because you can just algebraically add them together. So, but it's a very subtle thing, and it's kind of missing, or it's a bit cumbersome for what we intend, because that's implying the algebra of real numbers with weights on the graph requires that you have some kind of engine that does multiplication outside of the hypergraphs, right? It's like you need to know how to do real multiplication in order to do real matrix multiplication beyond the graph rewriting, because you're defining your graphs as weighted graphs. So that's why we don't immediately want it, right? Because you need the whole point is to have graphs that are computational minimally, right? Like they are the computational.
Depends when you interpret graph as weighted. Like every graph is weighted in like two value.
No, sure, but okay, sure, but the point. No, I understand what you mean, but the point is, if you want, so your computational system is going to express some kind of computation, right? Your rewrite rules are going to express some kind of system, right? Some kind of the SK combinators or whatever, right? So the idea is that if you can impose something that only depends on your substrate, which in this case are just graphs, which are Boolean matrices. I mean, graphs and Boolean matrices are mathematically indistinguishable. That's what they are, right? So you are already saying you have Boolean algebra in the background because you have Boolean matrices or integer multigraphs, right? You have integer value matrices or something like that. You have those already in the background as something that you can use. But if you have to put real numbers in the background, as someone that is getting into analysis with the Langlands program, you will know that that's not trivial at all. Like, I mean, if you want to do it in a computational way, real multiplication is not trivial at all, right?
Yes, yeah, I get it, but yeah, I'm just looking at it from more like general point of view, you know. So you put whatever you want inside. Like,
Yeah, no, makes
here
sense.
you need to know how to add 1 modulo 2, basically.
Yeah.
Yeah.
Yeah, that's the point. All right, I think we should move on.
Well, I guess I won't take too much time. I'll just show this kind of function that I made today. A requirement for continuation on the hypergraph, tensors and so on. So, as Carlos said, for our tensors, we have to contract our indices, right? Ternary contraction, quadrilateral, whatever. How many indexes you have to contract it. And turns out the Einstein summation is a nice function that's already in the resource repository. Can do that, right? So I was under the impression that it could do that kind of contraction, but I tried it today and it failed. So I had to patch it up. And now it's I published it into my cloud, and now it's more powerful than it were before. Now it can contract multiple indices of arbitrary number of tensors. Well, it's not as efficient as before, but it can do at least that, right? And it also supports this usual notation that you see in Python packages. Like, if you've seen Einstein summation in Python packages, it usually uses this kind of strings. If you have 2 tensors like this, all of those are square matrices 3 by 3, right? And you want to contract a second one, you can just either write it like just describe what indices are for each of those tensors. And when you have the same index, you can name it whatever. Instead of 1, 2, 3, 2, I could use the actual symbols like I, J, right? K, J, right? Because this is the same symbol, the same integer. Those are the indices that are going to be contracted, right? So, and what you get back is, in this case, is a matrix, because I contracted a code.
So, Nick, quick question about the formatting there. So you have a lists of indices.
Yeah, for each of the corresponding tensors.
Right, so this thing, rightly, in my opinion, doesn't distinguish in principle about covariant, contravariant indices or anything like that. It's just indexed, right?
No covariant, no covariant.
Sure. Okay, perfect.
It's like, and now, before you couldn't do a thing like that, right?
Yep.
Now you have 3 the same indices, and now it contracts both of them together, and now we get the vector.
Cool.
And one of another feature that you can do, you can also explicitly provide what is the output index going to be, right? In this case, it's the same as here, but you can actually have arbitrary multiplicity of those, so that it kind of.
Can you enter new indices that way?
Well, it doesn't make sense to have a new indices.
No, it does, right? If you want the output of your operation to be, larger, you just.
Well, that's how you do it, right? Here on the left-hand side, you provide all the input indices. You name all the input indices for all of your input tensors, right?
Sure.
And on the right-hand side of your rule, you provide all the output indices. If the indices are the same on the left-hand side, they're all being contracted,
Yeah.
right? But if there is, after this contraction, there's not enough indices to like build up the output index shape.
Yeah, but then
it
you
expands.
cannot introduce new indices, right? That's the answer.
Yeah,
basically.
there's no indices. Yeah.
Okay.
For example, I still can use J.
Sure.
That way, one of those J is not going to be contracted.
Sure. And another thing is, can you do? Because this is the contraction operation with arrays that we've discussed with tensors. But can you do this non-Einstein product basically, which means that you're multiplying. So it's basically the generalization of the Hadamard product, but for specific indices, right? So when you have two vectors of the same length, you can just Hadamard it, which means you just component-wise multiply, right? But if you have three vectors of the same length, you can just component-wise multiply. And you would write the vector would be written like in the Einstein summation. If you have three vectors A, B, C of the same length, you might write A sub I, B sub J, C sub K, and that's kind of the tensor product. That's IJK, 3 matrix. But you could also do AI, BI, CI, right? That's a 1 matrix. That's a vector, and it has by components the three-way multiplication of the scalars, right?
Well, I'm not sure. I have to think about it. What exactly are you asking for? It's like,
so when you do
the reshaping of the tensor after this summation.
So it's basically you have in the case of the simplest case of two indices, right? If you imagine the diagram that represents the indices, you have I, P, J, right? So P is the common index that you're contracting, right? So you have this kind of graph diagram, I, P, J, right? And so if you represent on the edges the elements of your matrices, you have A, I, P, B, P, J, right? So the idea is you can write algebraically, you can write this formula with the sum sign, right? And you sum over P, or you can just leave P free, right? To run. So the term that you sum over, so AIP times BPJ, that term, that's a 3 matrix, right? Which is the fact that is in terms of the rewrite rule correspondence, it's a rewrite rule that is from a wedge of sides, right? From a V motif is writing a triangle, which is the triangle that is the ternary relation that says among these 3 there is exactly this motif, right? And it remembers the 3 of them. When you sum over all of them, you're basically forgetting about the intermediary and saying there was at least some, or there were these many intermediaries between these I and J. And that's why you end up with, again, I and J. So the reason why we need this way of multiplying, where you basically don't sum, you multiply, but you don't sum, right? Which is the Hadamard product, is the generalization of the Hadamard product for general tensors, is because in this rewrite sense it's very natural. It's just contracting is kind of going one step further, where you say no, delete information. I don't want to know if there was one or there were this many, but I don't need to know which ones exactly, right? So it's in this sort of like.
No, I'm not sure. It's like it seems like if you write an example, I think I understand.
Yeah. Okay.
Like you can contract. You don't have to contract anything, right? Like
Okay.
For this kind of matrices, you can name it.
But that's
KL.
yes, and that's the tensor product, right?
Yeah.
Yes, but there's something in between contraction and the tensor product, and that's what I'm telling you.
No, I don't get it. What is it in between?
The Hadamard product, which
What
is
is the Hadamard exactly?
the Hadamard product is index-wise multiplication, right? It's like component-wise multiplication, but only along certain indices or a certain index.
Oh yeah. So element-wise.
Element-wise, yeah.
Right. That's what.
Yeah. That's kind of in between, because you're doing sort of a element-wise thing. You're multiplying, but you're not adding over, right? So it's kind of an intermediate. So you want that whole range. The whole range is just multiply or sum, and in any combination. So if you can also only sum component-wise. This is nothing preventing you from doing that. It's very weird. Like almost nobody does it. I guess I'm sure in somewhere in machine learning and deep learning.
I think in machine learning they usually refer to some kind of batch formation or something.
Exactly.
Because you can only sum or multiply tensors when they of the same shape, right? So you have to at least pad it with some one-dimensional thing, then you can.
NumPy also has broadcasting. So if you have if you have a singleton dimension, it will sort of expand it out to match the other.
Yeah, broadcasting is also a very natural operation, but it's not so much algebraic. Like it's if you ever have if you want to know what I think should be there, it's in the paper, this array algebra paper that Tali and I wrote, that has all these basic operations. I mean, it's
we have a notation for that.
Well, the notation was hypergraphs. That's the thing.
Well, is there some simple notation like that? How would you?
No, but that's the whole point. I mean, I'm glad that you mentioned notation, because the whole point is that when you're getting to the business of having arbitrary arrays and you want to do this arbitrary algebraic operations on indices with assuming arrays are valued over some ring or some semi-ring. This whole point, our whole observation, what we call plex algebra in that paper, called it plex algebra from simplex, because it was like without the simplex part, whatever. Like the entire take-home message of this plex algebra business is that you can use hypergraphs to represent array operations. It's not. You also have this idea that you can take hypergraphs and make them arrays and blah blah blah. And there's this nice sort of like self-referential fact there, but this entire point was that it is a notation for array algebra.
Well, this is the hypergraph notation. here, two edges.
Yeah.
Right?
Yeah. That's it.
How can you use it for this element-wise broadcasting?
So in our case, it was just labeling the vertices, because you had two options. I mean, our notation used graphics on hypergraphs, obviously, right? I mean, that's what notation does. You kind of like modify symbols and things like that, right? So we had like, if your hypergraph has vertices that are naked, then they are just so-called incidence products, which are these Hadamard products, these sort of like element-wise products. If they had like a dot or they are shaded, then they are contracted. If they are, if you have an arbitrary edge, you can always create. So you can always duplicate some vertex, just copy it, right? And then you can broadcast, because you can essentially sort of extend. So you go from one line to a triangle, from a triangle to a tetrahedron, and things like that. So it was meant to be this kind of three-dimensional notation, or graphical in the sense of graphs and hypergraphs, like hypergraphical notation.
Yeah.
But anyway, that's just it was just a comment to know that we should be able to have a very direct way to do this incidence sort of element-wise operations. And
I would love to make some version of Einstein summation, call it something different.
Okay, let's meet tomorrow and we'll make it in 5 minutes. It's really quite easy. I think it's going to be very easy. Like, let's not use more time here. I think it'll be quite easy.
Fine. then it's over. My presentation is complete. I can also show some nice GPT stuff. and I've been playing with some voice generation.
Oh, nice.
I cloned Steven and cloned James. We can make them rap.
Wait, have you done this already without?
Yeah.
Wow, that's beautiful. You cannot say that and not show something.
Oh, please don't show anything. Yeah. Richard, I know you have some research you wanna.
Oh no, actually, I've lost it. I mean, it's gone somewhere. I think. Over to Nick.
But did you do the deep fakes as well?
Well, maybe later. For now, just voice and careful prompting.
So wait, so you can have a conversation with Steven now?
Yeah. kind of.
We should, James, we should sell this. People who
Sure.
ask emails like,
Immortalization.
you have now.
Digital immortalization of people using language models.
Yeah, it was a long time coming. I mean, it's been some time since this.
Famous people is quite easy. You don't have to prompt it, just like pretend to be Stephen Wolfram. It's just
But there can't be that much
Actually,
data on me, surely.
Well,
I
there's
mean,
a lot
we do all
in
these
the last few months.
we do these live streams, but it's not like I'm,
it has to be annotated, like it has to do speaker detection so it knows it's your voice. But that's trivial. But yeah,
well, I just took James's TED talk. It's enough to clone your
oh
voice.
God. I had like 2 hours of sleep when I gave that TED talk. Well, I guess the good thing is I can stop taking responsibility for things that I say online now, because it could may as well just be some avatar of me. So
Just wait. Those are 11 labs. It's quite nice. State of the art text to speech system. It's cool.
Nice.
Oh, Richard, dear Richard, you have something you want to show, right?
We're letting down the viewers. Means of distraction is saying, are you saying I can ask Stephen Wolfram bot questions now?
I mean, you could ask him questions anyway. His email is public, and he has a lot of live stream.
Will he get mad when people call him Steve? You check that?
Richard.
Oh, is it really me, or just jokingly me to deflect the?
No, it's your go.
It's really both,
Yeah.
both, man.
Sorry, I didn't quite get the cue there. This will be extremely brief. I just have a few things. Let's see, get this correct window up. Let's close the Chat GPT where I just told it pretend to be Stephen Wolfram. I'm closing that tab, and yeah, we got these things, and right, ready to share. So yeah, last time I didn't like some of the sort of program space visualization, so I decided to look at some more. And in this case, at the end here, I'll just jump to the end and skip over these other things. It's a 3 instruction, or is it? Oh, sorry. This is a 3 instruction setup, and we're just sort of looking over the whole space over some range, some narrow range, so from 1 to 4, in both the numerator and denominator. And as I've remarked in the Discord, you have some duplication, like. Okay, not this example, but like, 6 over 3 is equivalent to 4 over 2. So you would have certain points which are kind of duplicated, which is unfortunate. But yeah, some sort of interesting structures seem to emerge. This is again the 3 instruction case, which does go up to 6 this time, with some random initial state that I've just picked out of a hat. And in this case, we're looking at like the program length. And yeah, you do get some kind of interesting self-similarity. Not that that's a key, that might be a kind of trivial consequence of some sort of numerical thing that's going on. But for example, you have these sort of like large blocks missing in a large shape, which is also repeated in this lower structure. And then there's quite a bit of sort of variety in terms of the program length. Over this little domain here that I've looked at. So that was just something I did sort of immediately after the last meeting. And I started thinking a little bit about what Carlos was saying about spaces in the sort of true sense, and thinking about in these little register programs or even imperative or some block of assembly code or whatever, so not in the rewriting world. In that world, you can have sort of permutation of sort of groups of instructions, and we were discussing these decompositions, and Jordan normal form came up because I had to use it for something. And it did make me think a little bit about how sort of some ordered sequence of instructions actually does have this notion of these subspaces, I think, but that's just a little idea in that there will be portions of programs which can be sort of permuted and others which cannot. And so, yeah, I think there's a connection to this idea of these subspaces, these blocks in a Jordan normal form matrix. Okay, and then yeah, somebody asked this question, which I found through just sort of asking my own, and it was the sort of the space of all imperative programs. Although the distinction of it being imperative, functional, logic, whatever, is kind of irrelevant. But somebody dropped a few interesting references, which I decided to have a look at. One of them is Dana Scott, is the lattice of flow diagrams, and then he mentions you can think of imperative programs as generators of possibly infinite transition systems, which will form a co-algebra, and so I will paste these in our public Discord. But there's some very interesting sort of notions that are touched upon here, which I will just sort of pictorially sort of present by going through, and maybe I will sort of remember some or pick up on some points here. What was so these are actually control flow, so they don't deal with data flow whatsoever. Here's some kind of infinite he talks about nested loops. Yeah, here's some nested loop structure thing. And this was all motivated actually just by, let me go to where was it? Oh yeah, this portion of one of the Conway talks, and in his actual paper, he sort of shows a sort of graphical representation of the Fractran programs, and then I sort of pulled something out of one of Minsky's publications, and there's a section where this section here where a single register Minsky counter machine. It seems to be that's the kind of all. I mean, I say all, but what Conway has done is basically taken that and sort of made it numeric by thinking about the depth of each register as the natural number. So yeah, and just to explain, these Minsky machines are essentially finite state machines, but along each transition you can sort of update some arbitrary number of registers by pushing and popping into them. And he has some very interesting constructions in his publications, and he shows how you can compile from one into the other and so forth. But yeah, that's why I wanted to look down this control flow picture. And so anyway, I'll drop that reference. And then this other one here seems very good. Introduction to Coalgebra, Mathematics of States and Observations. And well, it will take a bit of digesting, but it seems very kind of categorical, diagrammatic, and so forth. I really don't have much more in terms of what I think is suitable for this meeting. So
I was going to say it was nice to see. Go on.
Well, does any non-deepfake, non-virtual person have any feedback or any questions for Richard?
Or just points or ideas, anything.
I believe I'm not a generated entity.
Carlos, you're on mute, buddy.
Okay, I was saying I believe I'm not a generated entity, but apparently I was. So no, I'm glad to see this last paper, because when you were showing the previous one, it's almost like you showed a snippet of computer science and mathematics history, because you see this, when you see this compositionality of these circuits and things like that, you're immediately thinking of categories and monads and things like that, and all those sort of structures. And then the next paper, you naturally go there. So yeah, I mean, from the distance that I take from that line of work of yours, I think it looks pretty good.
yeah, there's a lot of things I have to look into and learn about this area. So this seems a lot more, yeah, a lot more modern. Whereas I think, yeah,
Yeah, that one looks more crafty. Usually the balance you have to pay. In more categorical is less crafty, and then
yeah, yeah. This is also 1970, so a lot of this stuff hadn't really been sort of defined. I think by that point, it's kind of a lot more.
I think most of maybe it kind of existed in some people's minds, but it was definitely not
Yeah.
spread at all.
And not named as such. I mean, of course, it's like, you have abstract algebra and so forth. There's a lot of things in that field which overlap with the
I
kind
mean, in the
of
70s,
categorical.
you already have some category theory going on.
Mhm.
I mean, there's actually a fair amount, but it's very confined in a very small community. It's not widespread at all.
Mhm. Okay.
I mean,
Yeah,
it's funny how
that's what-
category theory took almost like 40 years to permeate outside of hardcore algebraic topologists and algebraic geometers and some early category theorists, differential geometers, things like that. But yeah.
Yeah, and yeah, just in closing, just more. I find these kind of interesting, and I'm wondering how we could think of other views on this sort of program
Well,
space. And, yeah.
have you toggled the initial condition just to see
Mhm.
how much it varies?
I don't recall how long this one took, and I wouldn't risk doing it live.
Yeah.
But I have done. It's like you keep kind of adding sort of more dimensions to look over, and it becomes
Mhm.
sort of a cumbersome thing.
Mhm.
And yeah, some programs are quite sensitive to the way that the particular initial condition is set up. They just won't do anything unless you have a particular register or prime in the initial state. But yeah, there's some kind of interesting in this set of plots here. There are some things which actually remind me of some things I've seen in other places, maybe callouts related things. But yeah, there's some. Oh, and in some other question or something, somebody used the phrase like number theoretic rewrite systems. I actually quite liked that. Instead of numerical multi-way systems, I think sort of like number theoretic rewrite is maybe a better. Yeah.
More people will understand like arithmetic rewriting or something.
Mhm.
Number
Yeah.
theoretic
Number
rewriting.
theoretic rewriting, I think, is kind of a good term for this area rather than sort of numerical multi-way, because the multi-way kind of is a separate.
Well,
Yeah,
the
it's a
term
separate thing.
multi-way guarantees that less than 15 people on the planet will understand what it's talking about.
And these
Whereas
visualizations
rewriting is a broader research program.
Mhm.
Yeah.
And these are just looking at the single way. I actually did some of these plots looking at that multi-way construction where you don't care about the order in which you apply the multiplications or the fractions or whatever, and they actually looked very similar to these. They presented the same kinds of structure, so it didn't make. So I think something is kind of hidden and needs to be extracted in some more advanced way. If there is anything in the multi-way case that's of interest, it certainly didn't show its face. Yeah. So instead of using this Fractran resource function, I used this sort of nest graph tagged with the select integer q list of fractions thing, and then looked at some of the properties on the graphs, like the number of vertices, number of edges, the ratio of those, and so forth. And they just presented very similar plots like this, actually. But yeah, rather than drag on, I'll stop there. There's not a lot more to say.
Well, I know Carlos has some somber Spanish event to go attend. I'm always amazed that we're able to actually cover everything people have to share within like just a little over an hour. I didn't really say much today, but it was nice just to see you all chat about each other's projects. I really do like this roundtable approach. Well, so for people who have been listening, if you want to attend tomorrow and listen to us riff about more general matters, everything from ecology, future of publication, answering questions about. I'm sure whatever Nick has been doing is gonna manifest itself in some way. But if you have anything that you want to hear us riff about, something that you think we might have something intelligent to say about, you can ask some questions. You can ask some questions on the. What happened to my computer? Oh, I'm still here. Oh, that's weird. Something happened with my monitor. You can ask questions beforehand. We can post some kind of prompts tonight in order to maybe solicit some questions from you all about topics that we think we might be able to say something about. And but yeah, we look forward to seeing you there. Any last words? That sounds morbid. Anyone want to any closing comments on this stream before we wrap up?
Last meal requests.
Actually, yes. Before we go, although I guess I would announce it tomorrow as well, but in case there's someone watching today who won't be around tomorrow, we have a poster to divulge. So how could I show this actually? Yeah, let me just share.
Nice.
Oh, that's fun.
So yeah, I was able to confirm with a few of the speakers, and things are rolling, and so I feel confident enough to advertise that the final week of April, so 24th to the 28th, we'll be running a workshop hosted at the Institute that will be sort of have sort of bookends on Monday and Friday with talks by some of the few, not many, very populous community investigating higher order tensors and tensor algebra and things like that. But I would say the main figures will be there in some capacity. So Eddie Nagang and Richard Kerner, Groucho as well. I mean, these are quite relevant names. Tali will be here as someone known for the Wolfram community, and we already mentioned today about arrays and all this sort of approach to tensor algebra and generalized tensor networks that uses hypergraphs more as a notational device than itself a phenomenon to study. But yeah, so if you're watching and you feel you have interest in this topic, we will be circulating this event with experts mostly, and it's a sort of a scientific networking event. But we will be live with the talks. We will be on Discord implementing some chat rooms specifically for this topic and so on. So I invite everyone to sort of come along and enjoy some hyper matrices and leave matrices behind once and for all.
Well, yeah, thanks for putting this together. This is this is good. Carlos described it as he was going to make some poster with some subtle Matrix movie, right?
I quickly, when I got into the graphic editing and I saw there was like the font and the background, because it just came up when I typed the terms. I was like, okay, I'm going all in.
Okay.
I dropped the subtlety here, and Let's just go, because I wasn't even going to, like, in the graphics program, if I typed two peels hands, there were like stock images of people with like a red and a blue peel just offering like that, just stock images, and I thought this looks so crap that I'm just going to take the actual frame from the movie and I'm just going to go full commitment to the aesthetic of the movie. So, because I mean, I thought, how many times am I gonna host a hypermatrix workshop where I can genuinely use a reference to the matrix for good use, right? So it's not many times in your life that you can do this. So I saw the opportunity and seized it. What can I say?
I tried Mid-Journey a little bit after the last meeting, but it wasn't so successful. I mean, it made cool stuff, but it didn't quite get the exact instructions.
Yeah, I mean, Mid-Journey is quite bad at getting very precise instructions.
Yeah.
But it always generates something interesting in some visual sense. So I feel it's been sort of almost overtrained for artistic interest in some kind of sense.
Definitely.
Yeah, I've gone to the point. I've generated so many Mid-Journey images now that I'm kind of like, I know this entity already. So like, you know the quirks, you know that how it looks, and I see like random pictures used somewhere else, and you know like immediately it's Mid-Journey.
Yeah.
I know this as in I know this steak doesn't exist.
Exactly. I know this image doesn't exist in anyone's mind.
Well. So we'll. Thanks, Carlos, for getting this together. Yeah, this is our first real workshop. We'll be holding it for a few days. We'll announce times, and we'll say a little more about the speakers and the talks that they want to give.
Yeah.
And so certainly on Discord we'll be promoting this, and maybe on LinkedIn and some other places. But this is a nice topic for our first workshop. So we hope to see you there. If you have any questions, if you want to know anything about it in advance, feel free to contact us. We'll be happy to hear from you. And looking forward to this after some planning and scheduling. We're really going to do it. So looking forward to that. All right, guys. Well, see you at the community forum tomorrow. And thanks for a jolly roundtable.
Same.
All right.
See you, everyone.
Bye-bye.
Cheers. Bye.